a quick introduction. So welcome everyone to the like the first full-length seminar. So we are very happy to have Sanghamitra Dutta. She's like a PhD student at CMU, and she's been doing a lot of work at the intersection of machine learning and information theory. And so she's going to tell us about some of her work, I think, regarding fairness, privacy, and reliability. And she is a recipient of like the Gates Presidential Fellowship, and I'm not sure exactly how to pronounce it, but like Axel Burney Presidential Fellowship.
Yeah.
And she was also a Honda Young Engineer and Scientist Award. She's a recipient of that. And so we are very happy that you're here. And so she's going to talk about algorithmic biases. And I guess without further ado, let's get started.
Yeah, thank you so much for the kind introduction, and thank you so much for having me here today. So today's talk is about how do we make machine learning algorithms lawful? Towards answering this urgent question, in this work, we will arrive at a systematic understanding of biases that are exempt and non-exempt using tools from information theory and causality. Now, to understand this talk, you do not necessarily need a prior knowledge of information theory in particular, and many of these concepts can be interpreted in terms of statistical dependencies, which is what I'll try to do in the talk as well. And this is joint work with Praveen, Peter, and Professor Anupam Datta, and my advisor, Professor Pulkit Prober.
Also, I wanted to interrupt right at the beginning
Yeah.
so that this won't come up. So basically, in terms of questions, I will monitor people who've raised their hands, and at some appropriate juncture, I might just interrupt you. So you don't need to bother about that. But if you're comfortable doing this, that's fine too.
Okay, sure. Yeah, I think it'll be nice if you only tell me because I'm looking at the slides. So yeah.
Yeah, that's what I imagine. That's fine. Yeah. Okay.
Okay. So machine learning is entering onto almost every aspect of our lives these days, including high-stakes applications such as hiring. Roughly 40% companies are now using machine learning at various stages of the hiring process. So while machine learning models are undoubtedly great at learning all kinds of patterns present in the data, but blindly learning all these patterns can sometimes have unintended consequences, like propagating or even amplifying biases with respect to gender, race, etc. So Amazon recently scrapped this recruiting tool that showed bias against women. Now, these kinds of biases can also often lead to lawsuits due to violation of anti-discrimination laws. For instance, Facebook recently had to settle lawsuits regarding discriminatory ads. So all of this raises a very important question that how do we ensure that algorithms are lawful? Now, for every problem or application, it is very important to first understand what is a good measure of bias that connects with that particular application. And in this talk, through this one problem, I will demonstrate how one can systematically arrive at a measure of bias for a given problem. So, algorithmic fairness is an exciting field of research with several interesting works in the last few years. But it is still unclear if we are relying only on the goodwill of hiring companies to incorporate these ethical practices, or to what extent can machine learning models be made lawful. And while fair machine learning has received a lot of excitement, there's been little work on lawful machine learning. For this question, a good starting point is Title 7 of the US Civil Rights Act, which prohibits discrimination based on race, gender, nationality, etc. But this law has an important nuance that has implications for the machine learning systems being used today. That is, the bias is exempt if it can be justified by a business necessity. For example, code writing skills can be a business necessity in the hiring of software engineers. Similarly, weightlifting ability can be a business necessity in the hiring of firefighters so that they're able to lift victims out of a burning building. So, given a choice of business necessities, how do we know if the bias is exempt or non-exempt? And towards answering this question, our main contribution in this work is a systematic measure of non-exempt bias, which is the unlawful bias that is not justified by business necessities. Now, my outline for today's talk will be something like this. I will be spending most of my time on this problem of finding a measure of non-exempt bias and in the development of the measure. And next, I will very briefly discuss some other research problems that I've spent time on. So to start with, how do we find a measure of non-exempt bias, which is bias that is not justified by business necessities? So to understand this, let us first understand bias in the context of business necessities as per our recommended interpretation of law for today's machine learning systems. So consider a scenario of hiring editors for a newspaper company. We have candidates from whom we will be collecting a set of input features that go into a model and produce a decision. Now, these features could be things like writing score, academic institution, aptitude test, gender, etc. Now, to avoid bias with respect to gender, one might first choose to not include gender in the algorithm. But it has been noted that even if gender is not explicitly used, bias can arise if the other features are correlated with gender, which makes the final decision also correlated with gender. The legal term for this is called disparate impact, which refers to policies that affect one group of people more adversely than others, even if it is not intentional. But disparate impact has this business necessity defense. For instance, writing score can be deemed as a strict business necessity, really critical for an editor's job. So one may feel that the bias due to writing score may be justified. But on the other hand, the bias due to the other non-critical features may not be justified. And even features like aptitude test may not be deemed as a business necessity all the time, as in the landmark court case of Griggs versus Duke Power. So one might be wondering, why should we not use these non-critical features at all? But that is also not a good solution, because throwing away features could lead to a huge drop in accuracy because we also lose useful information. So our proposition is to use the non-critical features, but in a manner that they should not introduce any non-exempt bias. This leads to our problem statement that we have a set of features that go into a model to produce an output y hat. Z is going to denote the protected attribute like gender, race, etc. Now the critical business necessity features are denoted by XC, and all of the other features are denoted as XG. Now the question is, given a choice of critical features, how do we find a measure of non-exempt bias, which is the unlawful bias that cannot be justified by XC? Now, once we have such a measure or definition, the next question would be how to apply it in practice. And this kind of a measure could be used either as a during training as a regularizer with the loss function to reduce non-exempt bias. It could also be used for auditing trained models to detect if there's a non-exempt bias or not. But before we do all that, the primary question in this talk is, what is a good measure of non-exempt bias? That is, how do we define something that we only have an intuitive idea about? Now, to answer this, we propose an axiomatic approach to arrive at a measure of non-exempt bias. Now, in many definitional works, a measure of fairness is often proposed based on some implicit desirable requirements. But then there arise situations where a wrong measure of bias leads to misleading conclusions. A good example is the Berkeley admission scandal that many of you might be familiar with, where initially people thought that there's an overall gender bias. But a critical examination under Simpson's paradox showed that, conditioned on the choice of departments like medicine or engineering, there was no bias. Similarly, recent studies on GPT-3 have also reported that language models have really creative ways of exhibiting biases and can even mutate biases, making it difficult to detect. Even in the space of explainability, people thought that Shapley values are a great measure of explainability until this paper pointed out that there are a lot of issues with this measure. So, when we try to define a measure, uh, in this work, we adopt a rigorous axiomatic approach that draws inspiration from Shannon's approach to arrive at a measure of uncertainty. Where the first step is to write down a set of desirable properties or axioms for the measure of uncertainty, and that eventually leads to his measure entropy and gives an interpretation to the measure. So similarly here also, we will first look at some canonical examples and desirable properties for a measure of non-exempt bias, which will lead us to candidate definitions or measures that satisfy those properties that can be then used to perform case studies on real-world datasets. And these case studies also inform our examples and properties. Now, the significance of this approach is that these canonical examples help isolate really paradoxical scenarios in the context of hiring, where a candidate measure might might fail to correctly quantify non-exempt bias as one would intuitively desire. So, and a key tool that helps us in isolating these kinds of effects is partial information decomposition, which is an emerging body of work in information theory. So in essence, our main contributions are a measure of non-exempt bias that satisfies all the properties, which happens to be causal. And then we also propose several non-causal or observational relaxations of this measure that could be used in scenarios where the true causal model is not known. And in doing so, we expose the pros and cons of several candidate measures as well. So now I'll first start with why popular measure statistical parity fails to quantify non-exempt bias, which will lead to our candidate measures and desirable properties. So statistical parity is defined as follows. Again, a reminder that Z is gender and Y hat is the model output. So statistical parity says that the model is fair if the probability or fraction of acceptance for men is the same as that of women. That is, the model is fair if the output Y hat is independent of Z. To quantify statistical parity, an information theoretic measure is mutual information. While I include the definition here for completeness, it's not super important, and what you only need to take away is that mutual information quantifies the statistical dependence between Z and Y hat that goes to zero if and only if they are independent of each other. But statistical parity has a limitation that it does not enable exemption of bias. For instance, consider this example where Z is gender and there is a critical feature which is correlated with Z. And you have an unbiased general feature which is not correlated with Z. Now, both these features go into a model and produce an output. And it just happens that the output is just equal to the critical feature XC, which was correlated with Z. Now, in this situation, the output Y hat is clearly not independent of Z. So statistical parity is going to detect bias in this scenario. But suppose you're doing something like fair linear regression with statistical parity as a regularizer, then what would happen is it would reduce the weight or importance of this critical feature in the decision making, which may not be desired. So here the bias is introduced only by the critical feature. So one might want this bias to be exempt. But now we notice that conditioning on the critical feature exempts this bias. So if you recall, Y hat is not independent of Z, but interestingly, it becomes independent of z once you condition on the critical feature xc. Again, to see this, notice that if xc is kept fixed, there is no further variation in the output y hat with c. So this is an example where dependence is greater than 0, but conditional dependence is not. This motivates our first candidate measure, which is conditional mutual information. This is inspired from the concept of subpopulation-based statistical parity, which is defined as follows: that irrespective of the overall acceptance probability, among the candidates with the same value of critical feature, there should be equal probability of acceptance for both men and women. That is, the model is fair if the output y hat is independent of z, but conditioned on the critical feature xc. And again, the information theoretic measure for this quantity is conditional mutual information, which is again a quantity that goes to 0 if and only if this conditional independence holds. Now, a quick visualization of this on the adult data set to understand what's going on here so far. So we will see histograms of overall predictions as well as predictions for the candidates who have the similar value of critical feature. So when there is no fairness at all, we see an overall dependence with gender in the overall predictions, but the conditional dependence is less. Now, when we use something like statistical parity, the overall dependence goes to 0, but the conditional dependence is not. In fact, some conditional dependence might even be introduced. And when we use this conditional mutual information as a regularizer, the overall dependence is not 0, but the conditional dependence goes to 0.
I have a question.
Yeah.
Okay. So what is the feature, critical feature here? Or like
Oh, here the critical feature is hours per week.
hours per week. Okay.
But while this conditional mutual information has some nice properties and allows for exemptions, it also has some limitations. Now, this is a very important observation here that we make in this work, which points out a limitation of subpopulation-based statistical parity or conditional mutual information. That is, it can sometimes falsely detect bias, even when a model is causally fair. Now, to understand this, we'll look at another example. So this is the biased critical feature writing score. The simplest mathematical representation for this feature is something like z plus u, where z is the gender and u denotes the inner ability of a candidate. So the underlying causal model would look something like this, where z is the gender and u is a latent random variable that denotes the inner ability of a candidate, which is independent of z. But suppose that the company is able to distill out the inner ability of the candidate in another general feature, which is xg. Now both these features go into the model and produce and say the final decisions are taken only based on the inner ability. Now in this case, this model is causally fair because the output y hat does not vary with gender after fixing this inner ability u. This is the reference for causal fairness, which is also called counterfactual fairness, which is saying that the model is absolutely fair if candidates with same inner ability are treated similarly and not differentiated based on gender. And if there is like no causal, if the model is causally fair, then the question of exempt or non-exempt bias shouldn't arise. But interestingly, here this conditional mutual information measure is greater than 0 for this particular example. And it falsely detects bias even when the model is causally fair. Again, to see this, notice that here y hat is not independent of z once you condition on the critical feature. To see the spurious dependence, you see that u can be written as z plus u minus z, where this is the part that corresponds to xc. So if we fix xc, then the remaining part of y hat begins to show spurious dependence on z, even though in the beginning there was no dependence between y hat and z. So this motivates our first desirable property, that a measure of non-exempt bias M should be 0 if the model is causally fair. And we will again revisit this false detection phenomenon in our experiments. So this limitation of conditional mutual information motivates our second candidate measure, which is called unique information. Now, unique information is derived from a body of work in information theory that is called partial information decomposition. So before I formally define it, I'll try to explain it through Venn diagrams. So say mutual information is a measure of dependence between Z and Y hat. And let's say conditional mutual information is the measure of conditional dependence between Z and Y hat. And as we saw in our experiments on the adult data set as well, they both can be 0 or non-zero irrespective of the other, which is why the Venn diagrams look like this. Now, unique information is the common information theoretic volume between mutual information and conditional mutual information that goes to 0 whenever either of them go to 0. So it represents the unique information about Z present in the output Y hat that cannot be attributed to the critical feature XC. And the example we just saw before in the last slide is actually a scenario that lies outside this red region, because here conditioning introduced some spurious dependencies that was not there before. Now I'm going to introduce the mathematical definition of unique information here. But again, this mathematical definition is not very important to follow the talk, and even an intuitive understanding is sufficient to follow the rest of the talk. So the way I like to think about this definition is that it's a conditional dependence, but when the marginal distributions between zy hat and zxc are preserved, but the joint distribution of these three random variables are altered to remove these kinds of spurious dependencies. And this unique information satisfies the causal fairness property as well as other properties that we arrive at in this work. So unique information, it satisfies this property and resolves this problem with conditional mutual information. But then there is also one issue that unique information also doesn't detect, which is masked bias. So now I'm going to explain through an example what masked bias is. So let's say there are equal number of candidates with inner ability 1 and 0. And let's say the editor's job ad is shown to men with high inner ability and women with low inner ability. And it's not shown to women with high inner ability and men with low inner ability. So now because these fractions are balanced across both men and women, no bias is visible. And it might seem that the ad is shown to equal fraction of men and women. But examining carefully, this is discriminated against women with high inner ability who do not get to see the ad. So the mathematical representation for this example could be something like this, that we have a feature which could be biased, general or critical, but it's equal to the inner ability. And the other feature is gender. And the model does an XOR of these two quantities, which is the mathematical representation of this kind of a function. So this is a scenario where the statistical dependence is 0, but the model is not causally fair, because there is causal path from the gender Z to the output Y hat. So this example motivates a second desirable property, that a measure of non-exempt bias should be non-zero for this particular example to be able to detect these kinds of masked biases. So to resolve such hidden biases, we are now going to resort to a path-specific causal examination. Now, these two slides might get a bit detailed and causality heavy, but it might be sufficient to only take away that causality is needed to understand masked bias if you don't want to get into the details of these two slides. So the question is that, can we say that a measure of non-exempt bias is zero if all causal paths from z to the output y hat pass through xc? And as we'll see that this alone is also not sufficient because of confounders, as we'll see in this example. So we'll again have this biased critical feature and an unbiased general feature aptitude test that go into this model. But now this model does something weird, that it cancels out u from these features and only takes its decision based on z. So this is a case of bias amplification where seemingly less biased features are mixing to produce like a heavily biased output y hat. And because of this, both of these features have to be held responsible for this bias because they're mixing and amplifying the bias, which is why this bias is also non-exempt. So here, all causal paths from z to y hat pass through xc, but there's a confounder u, which motivates this desirable property that a sufficient condition for the non-exempt bias to be zero is that not only do we need the causal paths from z to y hat to pass through xc, but also that no latent variable has such confounding effects on xc and y hat. And all of these properties finally lead to this causal measure that satisfies all of these desirable properties. Here again, ux is the set of all latent random variables that is being partitioned into two sets, ua and ub, which is coming from the confounding aspect of the problem. And this complicated looking measure satisfies all of our desirable properties, some of which we've already seen, and also some monotonicity properties that we discuss in the paper. Now, this measure as such looks very complex, and it also depends on the true causal model. But one thing is that there is value to first finding a measure that satisfies all of our desirable properties, however difficult it might be to compute, because then it can at least serve as a benchmark for other observational relaxations or candidate measures, and also help us understand what they capture and what they miss. And also another point is that this observational relaxation unique information, it actually satisfies all of the other desirable properties except masked bias. And it is only to capture the masked bias correctly that we need to get into this causal formulation and come up with this measure. So again, it is also good to notice that this observational unique information measure is actually lower bound to this proposed candidate measure, and their gap represents the masked bias. And on this other side, we also have an upper bound which comes from the confounding aspect of the problem. And this gap denotes the kinds of spurious dependencies where we do not want our measure to be non-zero. So this measure finally leads to a non-negative decomposition of the total causal bias into exempt and non-exempt components. But we are also able to separate out the statistically visible and masked biases, which leads to a four-way decomposition. That this is the visible non-exempt bias, this is the masked non-exempt bias, and similarly, this is the visible exempt bias, and this is also the masked exempt bias. And this statistically visible non-exempt bias ultimately becomes equal to this observational unique information measure. Now, one side point that I would just like to mention is that this non-negative decomposition is actually a key difference between this approach and some purely causal path-based decomposition approaches that tries to decompose influences along a lot of causal paths. So next, we are going to look into some observational measures of non-exempt bias. Now, as we try to look into observational measures that could be used in practice, we find that no purely observational measure can satisfy all of the desirable properties. Nonetheless, if we want to find measures that can be used as, say, a regularizer in the loss function, we have to use observational measures that satisfy only some of these properties. So we have already introduced these two candidate measures, that is conditional mutual information and unique information. And the third measure that we introduce is somewhat of a heuristic measure where you also condition on some other features based on certain suspicions or partial knowledge about the causal model. Now, this can resolve some issues with these first two measures, but not all the time. And we will refer to this measure from henceforth as CMI and this second measure as CMI prime to distinguish between them. Now we are going to look into some very simple case studies to understand how to use these kinds of measures. We will first consider a scenario where the true causal model is known. There is biased critical feature and also biased and unbiased general features. And the historic labels are based on all of these features. So we first audit a model that has been trained with no fairness regularizer. And as we see, this output has all these four kinds of biases present, that is exempt and non-exempt biases, which can further be decomposed into masked and visible biases. But now we'll look at training using these observational regularizers. And one important thing to note is that, again, here we use the knowledge of our causal model only for validation. We do not use the knowledge of the causal model for training. We only train with these observational regularizers. And the causal measure is used just to see what these observational measures are doing. And this is the kind of accuracy and true non-exempt bias trade-off we get using these kinds of observational relaxations. So this is the point which is most desirable, like high accuracy and low non-exempt bias. And our proposed observational measures attain better trade-off between accuracy and non-exempt bias as compared to popular measures like statistical parity and equalized odds. So equalized odds is something that I haven't introduced in this work, but it belongs to another class of fairness measures that uses the true labels in their definition. But this has been criticized that it does not account for historic label biases that are already present in the past labels, as is the case here as well, where it fails to detect the non-exempt bias or do anything much about it and stays very close to the best no fairness classifier. Now we'll see some experiments where the false detection of bias phenomenon happens. So here the historic labels do not have any causal bias at all. So the model with no fairness also has very negligible bias. But we see that conditional mutual information and CMI prime falsely detect bias. And in an attempt to reduce that bias, they also end up reducing the accuracy of the classifier unnecessarily, which is not desirable here. But then here's another experiment setup where only this masked bias is present. And in this case, we see that there are scenarios where conditional mutual information or CMI prime are sometimes able to detect certain scenarios of non-exempt masked bias, though not all possible scenarios. So stepping back from all of this, to summarize, we propose these three observational relaxations of our measure of non-exempt bias. And they all have their pros and cons. Like unique information is a more conservative measure. It never falsely detects bias, but it can sometimes miss masked biases. While CMI and CMI prime, they can sometimes detect masked biases too, but they can also do false detection of bias. But with partial knowledge or assumption about the causal relationships, these measures can correctly quantify non-exempt bias. So to summarize, this work provides a systematic approach to arrive at a measure of non-exempt bias, which happens to be causal. But then it also proposes observational relaxations that can be used in training. It also points out another important aspect that conditioning on subpopulations or statistical parity based on subpopulations can sometimes falsely detect bias even when a model is causally fair. So this whenever we use subpopulation based conditioning, we have to think critically about the choice of these subpopulations or subgroups and what that choice represents, rather than try to do statistical parity over all possible subgroups. And then it also introduces unique information, which doesn't falsely detect bias, but it can sometimes miss these kinds of masked bias scenarios. And this also brings out some broader recommendations for lawyers and also for society. One of them is this work advocates for a strict business necessity interpretation of this disparate impact law, which says that all features that a model uses are not business necessity. For example, even say models today are like an entire resume is being fed to classifiers, or there are like 8,000 features being fed to a model to take a hiring decision. In these kinds of scenarios, there is a need for questioning the right interpretation of law and going for a strict business necessity interpretation where only some features are deemed really critical business necessities that are really critical for the normal operation of the business. And we also look into this, propose that we need to take into consideration opinions of lawyers, social scientists, as well as minority communities to determine these choice of business necessities, like what set of business necessities actually makes sense for a particular application. Now, I'm going to speak very briefly about some other research problems that I've spent some time on. So this is just like the second last.
Actually, so
Yeah.
before you move on, do you want
Hmm.
to just like pause if there are maybe
Yeah,
some
yeah, yeah, sure.
questions on this slide? This is probably a
Yeah,
good
yeah, yeah,
slide
yeah.
for people to ask. So any questions from students or someone else? Otherwise, I was going to ask a couple of questions.
So I've got a question. So I'm not. So I was trying to figure out how to phrase this the right way. But so it seems. So I'm. So, so I'm a bit confused. I guess I didn't quite catch, like, if you're to run your techniques, you have to have this very specific labeling of all the features, and each feature needs to be discrete in some way, and it's either in one class, which is interpreted as like strictly important for the business decision, and then are all other features things that so um, so I guess I'm not quite sure exactly what to ask, but can you go over like exactly the ways you would need to know information about the features in order to do this sort of analysis, which seems very cool. I just don't understand exactly what is needed on the input.
That's a good question. So what time assuming you need is you have say a bunch of features going into a model, and a subset of these features, which could be say 1 2 features, 3 4 features, however many features, are decided as business necessities that are like reasonably necessary for the normal operation of business kind of features. And those are examples like code writing skills for software engineering job, or weightlifting ability in the hiring of firefighters, or even for other applications like education. Say you want to hire a PhD student in your group, it could be something like uh, academic record could be a feature which is determined as critical business necessity for the group. But there are other features like say GRE TOEFL score, or how is your English, how good is your communication skills. These are other features which might contribute to accuracy, but those are features that are not deemed as like critical business necessities that are necessary for the operation. So that's a kind of splitting across features we need for this approach. But what it enables is that when we do not have any kind of feature based decomposition of feature based splitting, and we just use a fairness measure and use it as a regularizer with a loss function, which doesn't enable these feature based exemptions, those kinds of models can sometimes reduce the importance of these features a lot in your decision making if the feature is biased. Like say weightlifting ability, if weightlifting ability is say the only feature which is contributing to gender bias, the model you learn might be something that has very low zero weight or 0.01 weight on this feature weightlifting ability, which might be sometimes undesirable for businesses. So we have this splitting where you have a subset of features whose importance you want to preserve in some sense, and the remaining features are ones whose importance you don't want to preserve that badly. Like you would want to use them to the extent that they improve accuracy, but you don't want to preserve them that badly that even if they are biased, their weights should not go down in some sense.
So each feature needs to be explicitly scored one way or the other. There can't be any like a distributed representation of some features that's mixing of some of the, captures some aspect of what is critical and what is not, without an explicit labeling. You would not be able to use that because its features it's mixing those things already in some way that could potentially be problematic, and so you can't use that sort of information. Is that?
Yeah, so I think in this formulation, that is like the first formulation that I stated here, that is not doable. But I think we are currently looking into extensions of this problem, where sometimes in a neural network, a hidden layer representation might also represent a critical business necessity than like the input features at the first layer. So those kinds of extensions are things that we're looking into that are possible to integrate into this definition. But the problem statement, as I stated today, it doesn't allow for that yet. Yeah.
Great, thank you.
Suresh, go ahead. You have a question.
I'm happy to wait till Sanghamitra, till you're finished with your slides if you like. I don't have to ask it right now, so I'll leave it to you to decide. Would you like to finish, or I noticed you have 2 slides left, so I'm just wondering if you want to finish them.
Yeah, I can just go for them. Yeah. So these are some other research problems that I've looked into in this space. So in another related work, we examine this problem of, is there a trade-off between accuracy and fairness? And here again, we use some information theoretic tools from hypothesis testing that uses Chernoff exponents to quantify these fundamental limits between accuracy bias trade-off. And it also introduces this concept of ideal distributions where there is no trade-off. And in another related problem, I've also been looking into this problem of filtered bubbles in social media, also called echo chambers, which refer to like a state where an internet user is only exposed to content that they like and agree with, and they do not get to see the other side of the debate. So here the question that we ask is, can we use these kinds of fairness tools to diversify recommendations with respect to something like, say, Z's political inclination here or some other attribute of this nature? And how we can diversify a recommendation so that we have high accuracy or high performance, but still they're somewhat diversified and we don't get to see only recommendations that align with one kind of political inclination or one kind of attribute. And then before I started working on fairness, I've also spent some time on problems in distributed stochastic gradient descent, as well as on error correcting codes that has led to this area called coded computing. And I'll also thank all my collaborators without whom none of this would have been possible. And I've had the opportunity to work with people from different fields and also collaborate with people in industry and academia who have provided me diverse perspectives. So again, thank you for listening to my talk, and I can answer more questions now, I think.
Okay, yeah, thanks a lot for the talk. And you see a lot of people applauding, as you can hopefully hear. So Suresh, go ahead. Your first question.
Yeah, so let's see. So there's a number of things, I guess, but maybe one thing I'd like to focus on, I think going back to the very beginning, the premise, right? The premise that you can somehow identify these features that are critical versus not. I mean, if you look at how the sort of the discourse around disparate impact actually goes, right, in a courtroom, right? So this is often a negotiated argument, right? So basically, the plaintiff will say, hey, you're going to, we think you're discriminating against, us on the basis of, say, race or gender. And the company says, no, 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 I have this business necessity. I have this reasons for doing things this way. Then the plaintiff will say, no, in fact, you could have done something this other way and that you could have had the same outcome. And so there's this negotiated process by which this determination of business necessity comes in. It's not really formalized in any way. And I think what you're attempting to do is claim that if you could somehow separate out features as labeled as critical versus not, you could somehow solve this problem. But in actuality, you're never going to get that, right? Because these features are going to be sort of overlapping in a strange way. And I think there's been, if you go back to the earliest work on this, like going back to the work by Kamishima and others in 2009, 2010, which you probably should be mentioning because they also use mutual information. And I don't think you mentioned that in your slides.
No, I think I stated it in the mutual information slide, I think. Yeah.
Okay. Yeah, but then, and also work by Zemel in their work on learning fair representations, the work that we did in KDD on disparate impact, even the KDD 2015 paper, as well as work by Edwards and Storkey later, as well as some work that we had done in Europe's a couple of years ago. The basic premise is that you can try to extract out the relevant non-biased parts of a variable, essentially using information theoretic means. So all these papers, right, use information theory, but not in this kind of discrete way that you're proposing, but in a more sort of smooth, fluid way where they try to pull out whatever they can by finding alternate representation. In fact, the Zemel paper is called Learning Fair Representations already. So I guess what I don't get is why you would choose to, in my mind, to go backwards essentially from these approaches, which are not trying to partition the variables and are trying to actually just merely extract what they can, which is non-signifying for the critical, for the sort of problematic attributes, versus what you're doing here.
Yeah, I think that's a good question. So I think the motivation is that sometimes when we just do fairness without feature-based selections, the feature importance can go down. And that is something that may not be desirable in certain applications by the business necessities.
So I guess I don't know what that means.
By what I mean is, let's say you have two features. One is uh, code writing skill, and one is something else, which is not business necessity. And the code writing skill happens to be biased, and we use something like counterfactual fairness or total fair statistical parity, something like that as a regularizer. Then what happens is the importance of code writing skill can only significantly go down because the model also has some inherent like limitations, like the model can't do all possible representations. So among the class of representations that the model can do, it can sometimes reduce the importance of these critical features. So that is something that a business might sometimes want to prevent, that at these features, the importance of the feature should not significantly go down. And that has been, I think, one motivation. And another is like, I think it also gives flexibility to like both models and businesses to be able to like have, say, a kind of middle ground between some features being business necessities and some features being not, as compared to the other approach where in a sense all features are being viewed as non-business necessities, or that becomes equivalent to like the business necessity set being zero and all features being non-business necessities. And then it becomes like only on the goodwill of the businesses whether they are doing this rather than a legal like enforcement to do this.
Okay. Just a follow-up comment, I think, is that I think it sounds like you're articulating a particular almost normative point that you want to make, that you feel that it is important that these features not be downweighted in importance, even though they are related to these protected attributes, because in some other sense they are relevant. And I think that normative position is external to your method, but it's something that I think it's important to articulate, because I think one of the bigger stories we have in all of this is that the confusing the normative with the technical makes it very hard to properly understand what the underlying sort of principles are behind these designs. And I think it would be helpful to make that very clear, because I think you're articulating a normative position which one might contest, right? I'm not saying I should agree with you, but one might contest it. And then we have to have a better way to contest this point of view and understand how it's affecting the design. But I'll shut up there, so I want others to be able to ask questions.
I had a somewhat high-level question as well. Like, I mean, I think it relates to what something that Suresh was asking. So in your example of this, like z plus u being the like a critical variable. So in such a situation, I think Suresh would argue that u is what some methods try to get, right? So in this kind of a setting, so what is the ultimate goal? Is it still to keep the weight on z plus u itself being high, or is it somehow classification by just by u is your intended goal? So that I kind of missed. I mean, I know that you can quantify each of these things, and yeah, maybe I guess yeah. So you may not even be known and so on, but and yeah,
Yeah,
in the real setting.
yeah,
So
yeah. So you may
yeah,
not be known, that I agree.
yeah,
So yeah, I think the goal is to not lose importance, but also have some flexibility that if U is isolatable, it might enable you to do that. But if U is not isolatable, then the importance of these features should not go down, which are giving the U.
I see. And in such an, if you have a constraint like that, like the importance of certain features should not go down, then it may not be possible to do something, right? So in that case, do you want to say that, okay, you know, you have to live with a certain amount of unfairness or something like that? Is that,
Yeah, I think this is, yeah. So if say the unbiased features don't, the non-critical features don't contribute any bias at all. It's only say one critical feature that is contributing bias, but that critical feature is very, very important, and it's not possible to like extract its useful information while uh, like
right,
not losing the importance. Then yeah, I think for those kinds of
right.
scenarios, yeah, like the bias that is present is exempt bias, and the non-exempt bias is 0.
I see, I see. I see. So I guess maybe, yeah, I see. So one way to view is your work is that it gives a bunch of additional measures that you could kind of define. And so you could make formal statements like this, which could potentially be then used in a court of law, right? So I see.
Yeah, and also I think yeah, it offers flexibility. For instance, like I'm not taking the position of a lawyer to say this is businessy, this is not. That is a choice that I'm letting the courts do, but I'm providing a quantification that given this choice, we are able to
Yeah.
quantify exempt and non-exempt biases.
Okay, interesting. Yeah. Yeah. So I think that helps set Suresh's questions into perspective, for, at least in my mind. That, yeah. Okay. Good. So anybody else have questions? I don't see hands raised. So please feel free to ask. Oh, there's some text.
So I've got another question. So so as well as so it's established, right, that there are these so defining features which you're not supposed to use in things like so specifically hiring, right? So this was most of the examples you're giving in so so this like things like so different fairness in um, so representations used by classifiers appear in various ways, like other than hiring, such as the sort of thing, if Google is personalizing a homepage, it's going to personalize it in a different way based on different features it's collected from you, but there's not necessarily a legal standard of what is kind of you're allowed to use, what you're not allowed to use. Like, is it allowed to use my gender to try and predict what it's doing? But you might not want certain things to be shown for other fairness reasons. In a context like this, where there's not necessarily I mean, maybe there is a law precedent for this I'm not aware of, but if there's not a law precedence, like, does this framework still make sense to analyze it this way, or is there like a softer way of defining these features that would make sense in this context?
I think a softer way is definitely possible. And I think even without the legal motivations, this could be applicable to other kinds of scenarios. Like even that recommender systems that we were thinking, there could be some, say, topics which you are really passionate about. Like, say, you're a researcher in climate change and you would want recommendations related to climate change, no matter the political inclination. But there could be a lot of other topics, like, say, healthcare or uh, economy, finance, where you would want to hear both sides of the debate. So that is the philosophy with which I'm coming from, that it might be, and even it could happen in a more softer fashion as well. Like you could, even when you're using it as a regularizer, you might have, say, a higher weight uh, to the regularizer with non-exempt bias and a lower weight to the regularizer with exempt bias, then like make it entirely zero. But you might want to preserve feature importances in different ways. So you might want to train with like biases that are based, that are inspired from a feature based splitting than like the overall bias.
I have one very basic question. So, does bias in ML come because of the model, the training algorithm, or because of the inherent property of data, or how we sample the data from out of the population? So,
That's a very good question, I think. So yeah, I think from the data, there are some fundamental limits on bias that we can arrive at. But a model can also do a lot of things to make bias propagate or even amplify. As in, this is a good example where one feature is z plus u and one feature is u, and the model is just subtracting out u and giving you z. So this is something that the model is doing through training. This is like a toy example, but this could have it happen in a sub part of the model. And for something like this, it is the model that has to be held responsible. So I think both data and model contribute to bias, and it also depends on what definition of fairness you are looking at, like whether it's an accuracy based definition or some other definition. But
also
I think,
how we sample the data, there can be bias too there. Like out of the entire population, how we sample the data,
mm,
like we should be unbiased towards sampling. That can also bring an inherent
yeah, yeah,
bias
yeah.
in the entire
That's,
thing.
yeah, I think these kinds of causal papers, they assume that the sampling bias is embedded in the causal model. But yeah, I think that is true, that if you change the sampling, then it could be like a domain adaptation kind of problem, that now the new data that you have is not drawn from the same distribution as the data on which you were trained on.
So this kind of work, this focuses on the model aspect of bias, and
Yeah, yeah, yeah.
the statistics people maybe deal with those the other biases that we are discussing.
Yeah, yeah. If you specifically want to think about this domain adaptation kind of thing, yeah, this doesn't take into account domain adaptation.
Okay, thank you.
I have a question.
Good.
So so you have this exempt and non-exempt bias. So my one question is like, if somebody already know like what is the important features, for example, like writing for an editor job, and so why don't we have like a two-phase kind of thing where we forgot about first like just look at the exempt features and then decide the pool of things which we want to have, where we don't look at the bias and then took the other out of those samples of selected candidates and go for a second round where we basically impose fairness measures among those candidates to select. Why we try to do everything together in a one single way where we want to have no dependence, or don't want to decrease the weight of some features, but we may have we can decrease the weight of other features to have removal of bias. Why don't we have separate out the segregation process? Because anyway in your case we are having discretization of exempt and non-exempt features for doing your job, for
Yeah,
the
yeah,
whole process.
Yeah, I think that's a good question. And I think there is nothing that I have against it. I think that is perfectly doable, but it just needs the knowledge of critical and non-critical ahead of time. So, uh, like when we want to think of something this in the context of auditing, it might get more complex. But I think that is perfectly doable, what you're saying. Yeah.
All right. So any final questions? Okay, so if not, let's all thank the speaker. I mean, it's great that you could do this, and yeah. So yeah, I see a lot of applause. So yeah. So are you like graduating soon or something like that?
Yeah, I am
Just
very
curious.
close to graduation. Yeah, I'm on the job market.
Okay. Okay. Yeah. So we were targeting people in that level, so that's great. Okay. Yeah. So yeah, I mean, it was a very nice talk, and so yeah, thanks for doing this.
Yeah, and thank you so much for inviting me. I also greatly enjoyed the interactions, and the questions were really nice questions and thoughtful questions. So thank you for that.
Yeah, no problem. Okay, thank you. So yeah, so see you all. See you for the others. See you all next week. And we have Michal Moshkovitz. She's from UCSD. She'll be talking next week. So I will send out abstract and things like that later in the week. Okay, so see you guys then. Bye bye.
Okay, bye
Thanks
bye.
again, Sanghamitra. Yeah.
Bye bye.
Bye.